So I'd like to start from an influation theorem of Pilar, and that's some funny way to reformulate his proof of the André-Oort conjecture for arbitrary products of modular curves. So I think I look at the n-time product of a modular curve. This could also be different modular curves. And you look at a sequence of special points. So what is a special point? Is a point such as each of the n coordinates, in this instance, is a CM point. I'll talk a little bit more about these notions in a second. And you assume that this sequence is any proper special subvariety, the intersection is finite. And the conclusion that this sequence is a risky dense. Okay? So just to put some terminology in place, such a sequence so that of special points so that the intersection with any proper special subvariety is finite, we'll call it generic. So I don't need to say it every time. And maybe I need, in this audience, also say something about order objects. So if you don't like modular curves, for the moment, it's a hyperbolic surface. It's not compact, but it has finite volume. And the points on it parameterize elliptic curves with some finite additional amount of structure. And these CM points are very special elliptic curves that have an exceptionally large amount of endomorphisms. And you should also think about this is not just a surface, it's actually a variety, so it's cut out by some polynomial equations. So you can say that a point is defined over some number field. The coordinates of the solutions are there. And then there is also a Galois action. And because these are actually algebraic points, there are finite orbits, the Galois action. And okay, maybe it's not helpful if you see these definitions for the first time. Otherwise, maybe a good analogy for a special point for our setting is to think about a point on a periodic geodesic in a hyperbolic manifold. Okay? And there is a reason for this analogy. It runs quite deep. Okay. So I also should say something about special subvarieties. So I'm not going to define them. I'm going to give exhaustive list at least for n equal 2. So what do we have? A special point. So if both coordinates are same points, then it's a special subvariety. Yes? Question? No. Also, if you take a product of a special point with the whole other guy, the complete curve, then it's a special subvariety. And the most interesting one are the images of these Hecke correspondences. So what are these? It's an embedding of a curve in a product of two curves. So it's embedding of some algebraic embedding of some modular curve, maybe of a different level in this product. There are countless many of them. And the archetypical example that you can keep in mind for the second is just the diagonal embedding of y into y times y. I don't need any algebra for that. And remember this is going to be our nemesis in the following, okay? We are going to fight them. So this conjecture is a strengthening of André-Oort. I just stated for product of modular curves, but you can go to any Shimura variety. So now you have this generic sequence of special points in a product of modular curves, and you look at the Galois orbits. So this orbit is finite in this setting, and you can attach a probability measure because it's a finite set of points. You just have the counting measure, you normalize, you have a probability measure. Then you assume that then you would like to think that if the sequence is generic, these measures equidistribute. So if you take a continuous function with compact support and you average over this finite collection, you go with I to infinity, you should converge to the integral with respect to this canonical uniform measure, which you normalize to be a probability measure. Okay? Unfortunately, so there was a lot of spectacular progress on the André-Oort conjecture lately. Unfortunately, the methods that you use there, which are rooted in transcendence theory, it's not clear how can they say anything about this, which is stronger. And also, maybe you would like to consider some intermediate conjecture, which is also interested, which is to consider analytic density instead of the risky density. So maybe you want asymptotic density in the analytic topology, which is common people are more used to, like me. Okay? So maybe you want that every open bow in this variety, that eventually the Galois orbit would hit this open bow. So this is something intermediate. So what do we know about this conjecture in this setting? So essentially, the only case we really know is for one modular curve. And that's, okay, this also has a long history. Maybe I'll start from the end here, but the beginning historically. So Linnik proved this conjecture assuming an assumption, and the assumption that in this sequence of special points, the CM fields are all split at a fixed prime. And he was able also to say that this assumption is redundant if you assume GRH, which is why, because his proof was actually effective. And it was effective enough so that if you assume GH, you know that there is a small split prime compared to the discriminant of this field or to the associated order, and the effectivity allows you to remove this assumption. Okay, but this has a splitting assumption unconditionally was only removed by Duke in the end of the 80s based on this breakthrough, analytic breakthrough of Ivanich, and using, at least on the face of it, very different methods from harmonic analysis. He checks Weil's criterion for equidistribution and uses some deep understanding about automorphic forms and bounding of Fourier coefficients. And there was so this is for the level 1 model curve, and there was a long chain of interesting developments in this, culminating also Michel much later treated the case of definite curves, and Chauveau, Zhang generalized this result and was able to prove over different number fields and quaternionic Shimura varieties such results for number fields, totally real ones. So if n equal 2, we know much, much less. So essentially, we don't know this conjecture for n equal 2. And the case that existed today is this result of Ellenberg, Michel, and Venkatesh from 13. And what happens here, they bootstrap the n equal 1 case to the n equal 2 case. So the idea, saying it quickly, okay, any Hecke correspondence, there's only finitely many points from the generic sequence in it. But if you fix a Galois orbit, it is contained in countless many different Hecke correspondences. And maybe if you are very lucky, you can find the Hecke correspondence such that its degree is small compared to the size of the orbit. And then by the n equal 1 situation, you should be close to be equidistributed in this Hecke correspondence. But this Hecke correspondence should become equidistributed in the product. So you can, so but for this you really need to be lucky, and this is not the typical situation. Also, this case, it has an analog, quite straightforward analog, if you consider function fields of a curve in finite characteristics. And then you have many more new tools available. And so this was considered by Schende and Zimmermann. Unfortunately, I'm certainly not an expert to say anything deep about the results. But so they apply Grothending-Lefschetz to these varieties, which are singular, which appear here, but they're not able to show that the main term is correct, but they're not able to show that the error term, contribution of low cohomologies, if I'm not confused, is actually. Yeah, I think I've written it, but I should have also said it. Unconditionally. Yeah, unconditionally. Mm-hmm. So that's the history. So what can I say? Unfortunately, not enough, but something. So that's the new theorem. So you have this same situation, product of modular curves. And you have this generic sequence of CM points. And now I'm going to put restrictions. Now, the first restrictions, I call them mild because there's good reasons to believe that they can be removed in the framework of the same proof. And the following, and then they'll come with the real restrictions. So for simplicity, we assume that they have CM by some order with fundamental discriminant. So all coordinates have CM by the same fundamental order, by the same order. Is that clear? So you have n coordinates for each point, and you want all to have the same discriminant. So this, in some sense, should be the more difficult case because then the orbit is as small as possible. Now come the big restrictions. You fix 2 primes, and you assume that all CM fields are split at both primes. I'll talk why this is important. And you assume that the Dedekind zeta function of this field has no exception of 0. And these assumptions appear for completely different reasons than generating small primes. Okay, then the conjecture holds. Okay, so how do we prove that? So maybe I won't be able to say so much about the proof, but I want to understand.
Yesterday we had a lecture where the guy assumed there was a fantasy.
Yeah.
It's nice to see a little bit of something that we believe is true.
Or at least this happens sometimes. Quite often, but it happens. This we know. Okay, obviously we would like to remove that. So these 2 assumptions are entrenched quite deeply in the proof, but in very different parts of the proof. And okay, so the first thing I would like to say that when I was working on this, I didn't think about André-Oort. Actually, I only thought about what does the theorem means in terms of André-Oort after speaking to Peter about André-Oort. And the proof already existed. Then I was thinking about torus orbits of points on these locally homogeneous spaces. So what happens because of class field theory, in this setting, at least the Galois, there's another group acting on for each CM point. There's an action by another Galois group, which is the Picard group of the associated order, which is, if you think about a point on periodic geodesic, you really should think about as the action of the compact torus rotating you around this geodesic. And now this is the same orbit, at least in some situation, but always related because the Galois action always factors through this torus action by reciprocity. And what I was talking about is this conjecture of Michel and Venkatesh, which is very closely related to this previous conjecture, which they call the mixing conjecture, but in dynamics we like to call it the Jennings conjecture. And now you have any form of PGL2 over Q, and you look at this space, divided by congruence lattice, divided by compact torus. Well, I didn't want to write anything about that there, so maybe I wasn't careful enough. You're really the most natural setting when you have finally copy of this from projecting from above. And they have, so Eisendler, Lindenstrauss, Michel, and Venkatesh defined a notion of toral packet, which is a generalization of this notion of a Picard orbit of a Higner point or a Gross point. And so this toral packets is a finite collection of points here, which comes from a single orbit of a torus in the Andelic space. And what happens, you can think about this subset of the product of two modular curves, or of two such spaces, which is not necessarily modular curve. So for each discriminant, for each order, you fix some element in the class group, and you look at this subset of Z, sigma iz, where Z runs on the orbit, which is exactly the situation, if you think we had before, translated to this setting. Okay, or almost exactly. You can also have an Atkin-Linear involution, but that's a compact thing, so we don't care about that really for equidistribution. And now we have a joint probability measure, which is invariant under this diagonal action. That's why I call it joining. And you need to assume something to conjecture that it equidistributes, because you can be stuck in some orbit of intermediate group, which is exactly the situation of Hecke correspondence. So except if sigma is the identity all the time, obviously, it's obvious what's going to happen. So this is the assumption translated into this language. So what happens, each integral ideal of the invertible ideal of the order in this class of sigma I corresponds to a Hecke correspondence which contains your orbit. And this is closely related to its volume and degree, and you want this to go to infinity, so it's not stuck in one. And then you assume what you assume. So it's the same conjecture almost, but in the language of toral orbits for n equal to. So, okay, I have 2 minutes, so I can say something. So how do we attack it? So let's start for something that was already known. And essentially, so Eisendler and Lindenstrauss proved the Jennings theorem for toral actions, very much motivated by this problem. And this is based on the theory of measure rigidity and entropy for toral actions. And what this theorem provides, because we know that the projection of any limit measure to each of the coordinates actually equidistributes by the n equal 1 case, if we assume that we have 2 split places, that gives us an action of a split torus of 2 split tori. Okay? Tori in homogeneous dynamics do not adjoin rigidity. So there are invariant measures which are not algebraic, which are very weird. But if you're invariant at the 2 split tori, then you at least conjecturally enjoy rigidity. And so any limit measure, in this case it's proven, any limit measure must be a convex. So you take any possible Wigster limit. And what you know is this amazing result that is a convex combination of very nice measures. So either what you want, or some combinations of Hecke correspondences and some translates of them, which is not too bad. So the real problem that was known for quite some time is that you need to find a way to exclude these intermediate situations, which is always a big issue when you try to apply measure rigidity to actual problems in number theory. So often people study orbits of semi-simple groups, so groups which have unipotence in them, and then you have Radner's theorem, and there are very strong tools to understand which intermediate groups appear and which not. But toral actions are really different, not only because they don't have unipotence in them. It's really, all these tools fail for fundamental reasons. So we need to find a new way to show that there is no intermediate measures, and that's the main contribution here. And the idea is, okay, that's not going to explain it really, but what happens is you want to measure the correlation between your orbit and some Hecke correspondence in the correct definition of correlation. And if you define it correctly, it has some extra algebraic structure to it. So it's actually a relative trace for this double quotient. And so there will be no spectral side to this discussion of relative trace, but there is a geometric expansion. And there is some nice expression for these relative orbital integrals as pairs of fractional ideas satisfying some relation, which will give you, in the end, a shifted convolution sum, a very short shifted convolution sums. And now you can try to do something analytic. Unfortunately, this sum is so short that the only method that I know how to attack it is using some slightly new sieve, but based on the well-known results of Shiu and Nair, and this is something very much inspired by the work of Bourgain, Rudnick, and Sarnak on the sphere, how to attack this sum. And this is where Ziegel zeros, you need them. Because when you use this sieve, you go to some logarithmic sums and the very short one, and you want to control this error term. So splitting condition appear here to know that the measure is not too wild, and Ziegel zeros is to actually show that you have no intermediate stuff, because I don't know how to do it anywhere else. So I think I'm even 1 minute over time. So thank you for listening.